Okay, we have what we call an opening address now. You know, on a crime scene, they have sometimes a person of interest. This is a person of interest to CIRES. David Fahey. Where are you, David? I hope you're here. Okay, there you are. Okay, David is a senior research scientist with the NOAA ESREL, or System Research Laboratory. He has been at that place since 1979, and that was the Aeronomy Laboratory originally, now called Chemical Sciences Division. He was a visiting fellow, right? And then joined NOAA. He's been a fellow of CIRES since 2003. He's interested in trace gases, aerosols in the atmosphere. He's worked a lot on ozone and a number of other subjects. I've been reading letters about him, so I know that he is a internationally leading atmospheric scientist, a very important person in his field. He's won the Houghton Award, the American Meteorological Society, and he's a fellow of AGU and has many other honors to his credit. Outside his science, he's been a big contributor to international committees that have been formed to address problems of the environment. He made a major contribution to IPCC and the Montreal Protocol. So with great pleasure and anticipation, I introduce David Fahey to you.
Thank you, Bill. Yes, I am a person of interest, and when I actually stop being a person of interest, I'm going to be careful of who takes my photograph. So it's great pleasure to be here this morning and to speak in front of so many CIRES friends and colleagues. I'm a good example, I think, of the cooperation between NOAA and CIRES. That 30 years ago this year I was a CIRES research associate myself, and then became a federal employee after that. But in those, right from those early years, I had CIRES people in my group at all stages, and now I have 10 of them. And so it's really hard to overstate how important CIRES is to NOAA, in particular for my research. There's just no way that I could do what I've done over these years, and no way that you would want to do it any other way. So I think it's great that we can celebrate that today, and it certainly has special meaning for me. And of course, when I do become director, this day kind of lays it all out as to why you would want to be director of this institute. It's really a fantastic institute, and Bill's remarks last night and this morning really kind of hit the nerve. The diversity and the quality here is just unparalleled. So I look forward, in fact, I'm humbled by the thought that I can do something like this. So this morning I thought I'd try and take a slice of my research and try and make it meaningful to this diverse group. Airborne exploration, if you had is a good two-word soundbite for my career over the last 25 years. And the word changing, airborne exploration of the changing atmosphere, is another good word that explains certainly where we've been in the last 2 decades and where we're going to go. When I first joined NOAA and started research, the word change really wasn't on our tip of our tongues like it is today. And it's kind of amazing how it just kind of happened over those years. So my content here is to give you a mixture of background and personal perspective and some science studies examples, and try and link to CIRES, and then make some summary comments. So this is a picture from the back seater in the WB-57 high altitude aircraft, giving you the view from 18 kilometers over the Gulf of Mexico. Really a stunning picture of the complexity of our atmosphere and some of the things we have left to do. So when many of you aren't familiar with atmospheric research aircraft, this is a little montage of the ones that you may want to take note of that vary from the aircraft down the road here at NCAR, the Gulfstream 5, all the way down to the bottom left there, the NASA Global Hawk unmanned aircraft. So these are all very sophisticated platforms in their own right, designed for particular performance, and we make use of them. These are the aircraft I've been involved with over my career, including the Gulfstream 5, the NASA WV-57, the NASA ER-2, Global Hawk, DC-8, and the NOAA P-3. So it's one of the pleasures of doing what I'm doing to be engaged with these platforms and the people that operate them. But at the end of the day, it's just a platform unless you put something in it. And so we as a community, starting here in NOAA CIRES, broadening it to NCAR, broadening it to the rest of the US, broadening it to the international community, have been very successful and accomplished at trying to fill these aircraft in a meaningful way. And the payloads usually divide into in situ and remote. In situ means we're taking air from around the aircraft into the fuselage or other payload area and making measurements of long-lived gases, reactive gases, aerosols, clouds, etc. Or we're doing it remotely with cloud and aerosol LiDAR or trace gas LiDAR imaging, etc. So just a few miles from here, you could find examples of all of these instruments and talk to teams that know how to use them. On the right there is the umbrellas that we operate under, the science goals that have been rather stable over the years. Atmospheric composition, radiation dynamics, and transport kind of include almost anything you'd want to do in the atmosphere to study it. But you go to the next level of detail, it's been climate change, radiative forcing, carbon cycle, aviation impact in my case, or air quality, ozone and aerosols, or stratospheric ozone depletion that take you to the specific kind of things that we've done with these aircraft. So we've been quite successful, and the we here really today means NOAA and CIRES. So why are these aircraft suite important? And one of the big reasons is obviously the access to the atmosphere that they provide. So here's this cast of characters on the right that I just showed you pictures of, plotted against altitude in your favorite unit there versus cosine weighted latitude. And in the middle there you see the tropopause from model analyses, how it varies over latitude space. Tropopause dividing the stratosphere from the troposphere, and a very key region of interest because of the gradients in chemistry and processes, etc. And you see how these aircraft really give you command of this space. And this space, when you can go to 20-some kilometers, is 95% of the atmosphere. And indeed, the Global Hawk, which you'll see later in my talk, can actually fly from one end of this graph to the other. And so it gives us purchase that is extremely enviable. And so if you look at the trajectory of what we've done in the past years, it's gone to almost every corner of this graph and done some very interesting things. And in the future, we want to protect that. We still want the ability to go to any corner of the world and take an instrument that we think is of interest. So this is my explanation of why aircraft measurements are of value. That it's really a combination of measurement quality, diversity, and location that lead you to discovery of atmospheric processes and their constraints, and increased understanding of our changing atmosphere. And when you have that, when you have discovered things and you have understood things, it feeds back into what you're doing on board these aircraft. And I think the key word, very key words to me is discovery. That it's one of those words that our program managers don't always like because it can't be scripted and it can't be predicted in advance. But yet we know it's the lifeblood of our science is to go out and discover things. So I think protecting that is extremely important, and aviation research, aircraft research is one very sharp edge of that front. By measurement quality, you can never separate a measurement from its investigator, the technique, the precision and accuracy that can be provided, or even things like the sampling inlet. Diversity, a lot of our energy goes into making the right suite of measurements at the right time and place. rather than just a specific measurement. And in real estate, it's location, location, location. You can have the best platform, equipped with the best instruments, but if you can't go where you want to go, you're not going to succeed the way you'd like to succeed. And that's what you just saw in the graph before that says we really know, we really have the ability to do that. The word change can be embodied in this graph, that one way of quantifying it and showing the complexity and comprehensiveness of our ability to change the atmosphere comes from this key graph from IPCC in 2007, which lists the terms that we know are very important in the anthropogenic forcing of climate, starting with CO2, going to the other long-lived gases, stratospheric ozone, tropospheric ozone, aerosols. So, of course, many of you know we spend a lot of time trying to do this. My point here is that aircraft observations and their interpretation contribute to our understanding of essentially all of these anthropogenic terms. And so it's really important to recognize that and to continue our investment in that direction. However, aircraft can't tell you everything. They're highly complementary to ground-based and space-based observations. And Walid Abdullati will tell us more later today about how and what you can get from space. So my group certainly has spent a lot of time trying to work on this word complementary to make sure that the value added that we provide is done so in concert with other efforts. The word change here again, changing times means changing your approach. You'll see that throughout this talk, that you have, as the problems change, the aircraft respond, the measurements we are pursuing do, the suite of payloads and the sampling strategies change. And this is really important. It's the flexibility that we build into our world. So our changing atmosphere. This is a picture from a seat on the NCAR G5 in 2009, taken by one of the participants in the HIPPO mission, included one of my research associates. It's looking out from 85 degrees north at 8.5 kilometers at a changed atmosphere. The moon's been looking down on this region for a long time, but it hasn't always seen this haze of pollution. And so, you can see not every aircraft can get to 80 degrees north. The importance here is this is part of the NCAR HIPPO mission, the carbon cycle effort led by Steve Wassey at Harvard, studying the emissions, transport, removal of gases with quite a comprehensive suite of gases and aerosols that you see there. CIRES had a big role in this from the Boulder camp, and my group in particular measured black carbon. What's unprecedented here is the pole-to-pole sampling in 5 phases over 3 years, where we'd leave Boulder, go to 85 degrees north, island hop down to 65 degrees south, and then make our way back. But not only is that unprecedented, but also is the fact that we're going up and down continuously. And so being able to sample the atmosphere with this suite of payload is part of our response, I would say, to a changing atmosphere. If you just take one snapshot and look at black carbon, this is showing it in latitude and height, and where you note the color scale here in the mass mixing ratio of black carbon, that's the amount of stuff that's there. It's a log scale. There's several orders of magnitude over that color range. And you see immediately the up and down, that it almost looks like a satellite picture to be able to see semi-continuously across such a fetch of latitude. And then how we take some forays into the stratosphere whenever we can. So you don't need to know much about black carbon to know right away that this graph and the other ones that we get from this mission will tell you a lot about black carbon. And once you know how this was done and put it in perspective, you realize there's no other way you could learn this about black carbon. You see the hemispheric gradient quite starkly here, which we anticipate because the sources of black carbon are in the northern hemisphere. And then even within the northern hemisphere, we see hot spots of cross trans-Pacific pollution coming from the east, from the Pacific Rim, telling us how black carbon is varying in the atmosphere. It's the second most important climate forcing agent. It was hidden on the graph that I just showed you. So we need to understand this, and my research associates have gone to some length and will continue to figure out how models best represent this. So another word of change. We're coming up with more and more clever ways to change our atmosphere. Coney just showed you some stunning pictures of the Deepwater Horizon oil spill. The importance here is, here's black carbon, major plume of black carbon, as well, of course, the fate of the other oil, the rest of this spill. So NOAA's and CIRES' response to this was a fast response. That this, our P-3 aircraft was participating in the CalNex mission in the Los Angeles area when this unscheduled event occurred. And after a lot of discussion at very high levels of NOAA and with the government, we diverted our aircraft to the Gulf to sample this oil spill region from the atmosphere, downwind of this spill where the volatile hydrocarbons were being released into the atmosphere. So it was a major kind of SWAT team response. We're doing forensics in the atmosphere, trying to learn something about something that didn't, whose initiation wasn't in the atmosphere. And we were quite successful. There were quite a number of papers that came out of here. It turns out that from sniffing these hydrocarbon emissions, you can actually back and do inverse modeling and figure out what get an estimate of the oil spill rate, which was quite consistent with other measurements. And this has been published. My group looked at black carbon and could quantify the yield from the surface burns that Coney showed you a picture of. And this was a fantastic experiment, if you had to accept it, to learn how organic aerosol is formed from hydrocarbon emissions, again led by Joost Gauw from CIRES. So this is a major coup to succeed in having a rapid response and doing such precise and quantitative and useful information, useful analysis of this event. And this has been recognized now by the governor in a high impact research award this year. It's going to 32 NOAA and CIRES personnel from Israel Chemical Sciences Division, 2/3 of which are CIRES employees. And the governor will come and give us this award next month here on campus. So right here, this is just a great example of the NOAA-CIRES collaboration and just how essential that collaboration, a well-running collaboration, is to successful things like the Deepwater Horizon oil spill response. Okay, the last science input here will be on water vapor, one of my favorite topics. My group spends about half its time on water vapor and half its time on black carbon. And we started out on the WB-57 aircraft, a fantastic high-altitude aircraft. We call it the truck because it can carry thousands of pounds to 20 kilometers and allow you to sniff the atmosphere from a number of payload locations. We're after water vapor. Here's the profile that's very canonical, changing from 20,000 parts per million, which is what you're breathing in this room, and you're probably very happy to do it. But by the time you get to 12 to 15 kilometers, most of that water's gone and you're down below 10 parts per million. We understand why that happens because water changes phase with temperature and drops out. But what's of interest is just exactly how much water is there when you get to these high altitude regions. And one of the reasons we're interested in this is its high climate sensitivity, that it's not intuitively obvious, but changing water vapor in this region of the atmosphere actually changes the surface temperature of the Earth. So we need to know how much water is there, and more importantly, how is it going to change with time. But the problem is that if you look at our track record as an atmospheric science community, we don't do a very good job. That in situ measurements here systematically disagree in this key less than 10 parts per million region. So if you fly 5 instruments on an aircraft like this, which we've done, in fact, NASA's flown more than 5 instruments, they don't all get the same answer. And that's reasonably unacceptable given the importance of this. So a NOAA CIRES initiative in my group in the last few years started a development project to come up with a new scheme to measure water vapor, chemical ionization mass spectrometry. But the distinction here was that we provided in-flight calibration, that when you were at in this key region moving at 200 meters per second on this aircraft, you would be calibrating. Turns out that no one else does that. And for such an important region and such an important molecule, we thought that time should come to an end. So we've successfully achieved our goal in 2010 by demonstrating this new CIMS technology on the 57, along with a suite of other instruments. And we're still in the interpretive process. We're about to submit some papers on this. But we already know that our ability to do in-flight calibrations with an instrument of this quality has already changed the conversation. And so another inside look at what this means. This is a WB-57 in the background. In the foreground is the pallet that sits in the fuselage bay that's holding 3 of my instruments from my group. One of them is the CIMS water vapor here on the right, which, by the way, as Coney just highlighted, won an Innovative Research Program award in 2008. And based on our success that I just explained, we won a CIRES Science Award last year. And I really, really like that arc, going from an IRP to a Science Award. I'm sorry? Yeah, I was reviewing my slides this morning and I thought, somebody's going to say that. and I'm embarrassed, and I thought for a moment I might Photoshop it in, but... And if those of you are looking very closely will see that I had to Photoshop in one of my guys. So you know I have the skill. But in my drawer in my office, I don't have any stickers of this size in the CIRES flavor, which is something as director I will change. So this is a huge success story, and if we're busy over there at NOAA, and if I didn't get this IRP, I'm not sure we would have gone down this road. I wasn't measuring water vapor before I got this IRP. And it's just amazing what has transpired that you couldn't have predicted by getting 30K seed money. So it's really amazing. This is the black carbon instrument that flew on the NCAR G5 and the NOAA P3. Here's the ozone instrument, probably one of the world's best ozone instruments. But it's the people I wanted to draw your attention to. This is a mixed CIRES federal group. There's 5 PhD scientists and 5 CIRES research associates. There's a mechanical engineer, software engineer, and electronics engineer. And this group can do essentially anything as far as I'm concerned. They're the reason all of these things got built. There's person decades invested in that simple payload. And so again, this to me is a picture, it frames the importance of the CIRES NOAA partnership, and you can see from my world, it's really essential. So the last slide, we'll be talking about the Global Hawk. This instrument, the little ozone instrument, is a new generation. It's made smaller, lighter, and more powerful than the one before, so it will fit on the Global Hawk aircraft. This instrument is too big for the Global Hawk, so we're building a new one that will fit based on its success. So the Global Hawk, to me, is the future. That it's the future of airborne science, it and its younger sisters, the smaller aircraft. The Global Hawk's the largest unmanned aircraft in the world. Its performance is here. It can reach 65,000 feet. It can fly for 30 hours. It has a range of 11,000 nautical miles, which I just showed you is halfway around the world. And it can carry a respectable payload, but it's not quite as big as the ones we're used to. So we have to be much more careful about what we put on it. Because it's unmanned aircraft, it has no pilots, but it's a system, not an aircraft per se. So this is part of the system. Guys mostly sitting in dark rooms while this aircraft's out on the runway. They only have a keyboard and a mouse. There's no other way to control this aircraft. And then there's a satellite somewhere that's bouncing what they would like to tell the aircraft through an antenna in the nose here. So this has been an outstanding aircraft, And I was part of the science team that kind of brought it into the Earth Science Quarter. Back in 2010, we did the first Earth Science missions with a white paint job and a NASA logo. It also had a NOAA logo on it. Working our way up to 29-hour flights, ones that went to 85 degrees north. Now there's one sitting, as we speak, out on the East Coast waiting to do surveillance on hurricanes that has NOAA equipment in it, has NOAA CIRES personnel on site. And so this has been rather explosive since we started this back in 2010. And we'll fly an ozone and water instrument in the Western Pacific in the next couple of years under a NASA Earth Venture class proposal. So, but for this future, these are key phrases here. The power this aircraft gives you doesn't come free. It's offset by its complexity. This is the most complex aircraft I've ever worked with. It took several years before NASA Dryden could build its way up to having confidence to fly this. But once you get there, it's worth it. The other feature would be challenging your imagination, that scientists don't know what to do with a 30-hour aircraft. They've only had 5 and 8 and 10-hour aircraft. So they have to learn how best to use the purchase of the atmosphere that this aircraft gives. And the only way to do that is to go out and do it, which we're doing quite well at this point in time. So in summary, I'll reassert that we have many powerful aircraft platforms, payloads, and science teams to meet the scientific challenge of our changing atmosphere. Indeed, it's an extrapolation of our work in the past. Seeking quality, diversity, and location in airborne measurements will lead to discovery and understanding in the atmosphere. We have many success stories to tell. I've given you a little sampling today, but it's just that, it's a little sampling. Changing times means changing your approach, and you've seen that with new measurements, new sampling strategy, and different aircraft, and just a hint about the expanding role of unmanned aircraft. And finally, congratulations to CIRES for 45 years of scientific contributions in support of environmental science at NOAA and CU, and I look forward to being part of the next 45 years later this year. Thank you for your attention.